Okay, class, this is the lecture that we were supposed to have on Friday. So we're supposed to be talking about binary. So here's the idea. So right now, what we normally do is we use 10 symbols to sort of communicate or write down a number, any number we want. And those symbols are, of course, 0, 1, 2, 3, 4, all the way over to 9. So there's 10 of those symbols. So that's when we want to write things down with the decimal system, or you can call it base 10, the base 10 system. But for computers, they basically work with lots of things that just have two states, on or off. So you can sort of imagine that you wanted to communicate with your friend and you only had like a light bulb. And so how would you count higher than 1 with a light bulb? That's basically what we want to think about. So you just I don't know why I committed to drawing a light bulb. I don't know how to draw a light bulb, but basically it could be on, or it can be off. So you could say, well, maybe off, that'll be 0, and then on, that'll be 1. But how would I represent 2? Well, I guess I need another light bulb then. So that's sort of the idea, but we're just going to jump straight into it and not worry about this analogy too much, because it might make it seem more complicated than it is. So basically in binary, we represent numbers with 2 symbols instead of 10. They are 0 and 1. Okay, so the first thing you learn to do with numbers is count. So that's what we're going to do here. So how does counting work in binary? Well, let's just compare it to decimal counting and sort of see what's going on. So the idea is when you count, when you get to the last symbol, so 9 is the last symbol, everything sort of resets. The next number after 9 is 10, but we should really think about it as a 0 being reset on the first digit, and then the next digit goes up by 1, whereas it was 0, now it goes up to 1. And then now the first digit goes up by 1 again until you get to the last symbol, which is a 9. And then when it gets to the end, the last symbol, you reset it to 0. Then the next digit goes up by 1. So now it goes up to 2. So for binary, we do the same thing. So 0, 1. And then now we're at the end. We're at sort of like the 9. You should sort of compare this to being at 9. It's not the number 9, but it's acting like the number 9. It's at the end. So what you do is you reset at 0, and then the next digit goes up by 1 from 0 to 1. Okay, so I don't want that arrow might seem confusing, so let me erase that. Then the next digit goes up by 1. Now you're at the end again, so it has to reset to 0, and the next one goes up by 1, but 1 is the end, so it goes and resets to 0, 2, and then the next digit goes up by 1. Okay, so it's the same as counting in decimal, where you just, this is sort of like when you get to 99, now they're both at the very end, so you have to set that to 0, set that to 0, the next one goes up by 1. Okay, but this is just, 0, 1, 2, 3, and 4 represented in binary. So it takes a lot of symbols to write down numbers in binary. Just to write down 4, you need 3 symbols. Okay, so that's counting in binary. That's the idea. So there is some notation to take care of too, which is, since we use the same symbols in binary and decimal, we want to be clear what we're talking about. So we could write something like this, a little subscript 10. That would mean that we're talking about decimal numbers. And then this with a little subscript 2 means binary. So in fact, these are the same thing. So 7, if you keep counting, let's see, let's practice counting. So now this goes up by 1, then this goes up by 1 and shifts the next one. Then that goes up by 1. Is that 7? Oh wait, maybe that's not 7. Never mind. This is 7. 1, 1, 1. Okay, so you could write something like this: 1, 1, 1 in base 2 is the same, equals 7 in base 10. So you could write something like that. Okay. Let's see. What are we gonna do now? Some more sort of just no language stuff. So in binary, each digit is called a bit. So that will come into play later, another day. But so what we could say right now is, for example, 7 requires 3 bits to represent in binary because I had to use 3 digits. So next what we're going to do is convert, because if I wanted to say like what's 103 in binary, you're not going to count to 103. You're going to want to be able to convert quickly. So next we convert between decimal and binary using some shortcuts. So the first is this. So let's start with a number in decimal. And what does this actually mean? This may be something you thought about a long time ago, or maybe you never thought about it. But this really means that there's 2 1s. There's 7 10s, and there's 3 100s. And even better, each of these are powers of 10. So this is really saying 1 is anything to the 0. So this is really saying 0 powers of 10. There's 2 of those. 1 power of 10, there's 7 of those. And 2 powers of 10, there's 3 of those. So this is another way to represent a number in decimal. Okay, so you may already have thought about that before, but in binary, it's the same except everything is a power of 2. So each place value is a power of 2. And so we could convert from binary to decimal very quickly using this property. So for example, 1 0 1 1 0 1 in binary, it means the same sort of thing as it did in decimal. It means that you have you have 1 2 to the 0. That's where this is coming from. Then the next digit, you have 0 of the next power of 2. Okay, then the next digit tells you you have 1 of the next power of 2. Then the next digit is another 1. So you have another 1 of the next power of 2. Then I'm running out of space here, but you have 0 of the next one. Oops. And finally, you have 1 of the 2 to the 5th. Now, if you know your powers of 2, you can do this much faster. So powers of 2 are, so 2 to the 0 is 1. Then 2 to the 1 is 2. 2 squared is 4. Then you get 8. Then you get 16. Then you get 32, and so on like that. So this number in binary right here, the other way to think about it is it's saying you have a 1, you don't have a 2, but you do have a 4, and you have an 8. You don't have a 16, and you do have a 32. And so you're just adding up the powers of 2 that correspond to the right digits. Sorry. So then once you finish adding this up, that's the number in decimal. So this would be 35 in base 10. Okay, so I'll do another example. There's many different ways to do this. So if you like it one way or the other, that's fine. I'm just showing you one way. So let's convert this to decimal. And again, we're going to do the same thing. So reading from right to left, there's 0, 2 to the zeros. There's 1, 2 to the 1. There's 1, 2 to the 2. And there's 1, 2 to the 3rd. Okay, so there's 0 ones, but there's a 2, there's a 4, and there's an 8 added together, for a total of 14. So that would be 14 in base 10. And there's an alternate notation that I just want to mention now. Which is using, instead of a 2, is using the letter B to stand for binary. Okay. Or there's this other weird notation, which is you put like an O with a subscript B in the front of the number instead. Okay, so there's other notations for this that we might use later. Okay, so that's basically how you convert from binary to decimal. So maybe I'll do one more. 1 1 0 1 0 1. Okay, so very quickly, because I know my powers of 2, this is a 1, this is a 2, this is corresponding to a 4, an 8, a 16, and a 32. But there are no 8s and there are no 2s because there's zeros in those digits, those bits. So very quickly, I can say this is 1 plus 4 plus 16 plus 32. Okay. And then whatever that is, 2053, I think, base 10. All right. So converting the other way is a little bit more annoying. I guess it's not more difficult, it just takes more time. So the first method is called the greedy algorithm, which usually just means like it takes as long as possible. It's just the brute force method is the other way of saying it. You just do all the necessary work with no shortcuts. So basically what you do is you pull out the biggest power of 2 that you can. So for example, 2, 4, 8, and 16, they all go into 48, but so does 32. 32 is the biggest power of 2 because 64 doesn't go into it, So 32 is the biggest power of 2 that goes into 48, plus the remainder. Okay, so what's left is 16, which also happens to be a power of 2, which is the best possible situation, because then now you can write this as 2 to the 5th plus 2 to the 4th, and no other powers of 2. So in binary, we could, read this out now. Once you write out all the symbols. So there's no 2 to the 1s, and there's no 2 to the 0s. Okay, but there's one of these and one of these. So in binary, we got to read it the other way, from right to left, or we could do it from left to right. So it would be 1 1 0 0 0 0. Okay, so there's no powers. There's no 2 to the 0s. That's what this is saying. There's no 2 to the 1s. There's no 2 squareds. There's no 2 cubes, but there is a 2 to the 4th and there is a 2 to the 5th. So this takes a while if you can't like figure out the biggest power of 2, or if it breaks down a bunch, it could be really annoying to do. So for example, if I do 125 in base 10, a 64 is the biggest power of 2 that goes into it. And then the remainder is 61. And then I have to do the same thing. So now the 64 stays there, but the 61, I do the same thing. So the biggest power of 2 that goes into here is now 32. So it's going to break into 32 plus whatever's left, which is 29. And then you got to do it again. Now the biggest power of 2 that goes into 29 is 16. So now the 29 breaks, now the 29 breaks down into 16 and 14. And then you got to do it again. Now 8 goes into 14. With 6 left over, now you got to do it again. And 4 goes into 6. And then there's 2 left over. And 2 is already a power of 2, so that's the end of it. So now in binary, you have a 64, a 32, a 16, an 8, a 4, a 2, but no 1. Okay, so this is your 2 to the something. It's harder, it's easier to count the other way. So this is saying that there's no 2 to the 0s. This is saying that there's a 2 to the 1, a 2 to the 2, a 2 to the 3, a 2 to the 4, a 2 to the 5, and then 64 is 2 to the 6th. Okay, so it can take a while if the number is even a little big. 125 isn't even that big, and it still sort of takes a while. Okay, so then the other method is, I wouldn't say it's any faster actually, but maybe it is. We'll see. Okay, method 2. You have to use long division, which it may have been a long time since you've done any long division. So for example, if you want to convert 48 in decimal, you just keep dividing by 2. Okay, so we'll leave this blank for a second. We'll do the scratch work down here. We're going to divide by 2. So it goes into it 24 times. And the remainder is 0. There's no remainder. So we have to keep track of the remainders for this method. All right, then we divide 2 into that number. So 2 goes into 24 12 times. Again, the remainder is 0. 2 goes into 12 6 times. Again, the remainder is 0. Remember, the remainder is what's left, and it goes into it perfectly, so there's no remainder. Okay, and then finally 2 goes into 6. 3 times, still no remainder. Oh wait, yeah, no remainder. But 2 into 3 goes into it once, and there is a remainder left. And then 2 into 1 goes into it 0 times with a remainder. Okay, so you go all the way until you get to this 0 here. And then the answer is just going to come from reading off these digits backwards. So it's just a nice little trick. So it's going to be 1 1 0 0 0 0. Okay, which I believe is what we got before, just to check our work. Where did I put it? Up here somewhere. Yeah, right there, same thing. Okay, so just another method for doing this. These two. 1 second. Okay, so after you learn to count, what do you do next? You learn about arithmetic. So next we're going to do that with binary. Whoops, let's go back to white. We can also do arithmetic with binary. So first thing you do is learn how to add. So to add, you do the same thing. You use carrying. That's the typical terminology for this technique. So if I want to do 1 1 0 1 plus 1 1 0, something like that, you just add down. So 1 plus 0, these two together is 1. These two together is also 1. But when you get 1 plus 1, you have to carry the extra 1 over. So 1 plus 1 in binary is 1 0. So you bring down the 0 and you carry the 1 to the next digit. So then again, you do 1 plus 1 is 1 0. So you bring the 0 down and carry the 1 over to the end. And you can also check it in decimal. So this is 13 plus 6 is 19. And real quick, we could check that this is 19. So this is 1 plus 2 plus 0 4s, 0 8s, but plus a 16 is 19. So good. Okay. So that's carrying. Same as what you learned in school for decimal number system. So you could do something more complicated maybe. But it really doesn't get too much more complicated. So 1 and 1 makes 0 1, carry the 1. 1 and 1 makes 0 1, carry the 1. 1 and 1 makes 0 1, carry the 1. Now you have 1 plus 1 plus 1. That's 1 1. So it's 1 carry the 1 instead of 0 carry the 1. Now 1 and 1 is 0 1, carry the 1. 1 and 1 is 0 1. Okay. So that's addition. What about what's next after addition is subtraction. Same as a decimal system, you use borrowing. Here's how we're going to do it here. If you know a different method, that's also fine. There's just something you have to remember, which comes in a lot, which is that 1 0 minus 1 is 1, because this is really saying 2 minus 1 is 1. Okay, so this will come in a lot in these problems. So let's see an example. Okay, 1 0 0 1 0 1 minus 1 1 0 1 1. Okay, so 1 minus 1, that's 0. That's not so bad. But the next one, 0 minus 1, is where you have to borrow. So you have to take the 1 out from this one, turn it into a 0, and give the 1 to this one. Now you're in this situation. 1 0 minus 1 is 1. Okay, now we're here. 0 minus 0 is 0. Then we're on the next one. 0 minus 1, can't do that. You have to borrow, but you can't borrow from the 0, so you have to borrow from the 1 over here. and give this a 1, 0. But then you have to borrow 1 from that 1, 0, which makes it a 1. And then finally get your 1, 0 here. So now, again, we're doing this 1, 0 minus 1 is 1. And then we're doing 1 minus 1 is 0. Okay. The zeros in the front don't matter. So the actual answer is just this 1, 0, 1, 0. Okay, so that's the answer. I'll do another one for you, just for more practice. Minus 0. Just gotta be careful to line it up nicely. Okay. So again, here we can't subtract. We borrow the 1. That becomes a 0. Bring it over here. Then we're doing 1, 0 minus 1 again to get 1 down there. Okay, then 0 minus 1, again, can't do that. Gotta steal the 1 from that one, and so that you can do it there. Okay, now you still can't do 0 minus 1. Gotta steal the 1 again from this one to get you 1, 0 minus 1 again. Now here, we're doing 0 minus 0. That's fine. The next one is 0 minus 1. Gotta borrow to do 1, 0 minus 1 is 1. And then 0 minus nothing is 0, 1 minus nothing is 1. Okay, so then that's that one. Okay, so up next is multiplication. We're not going to bother with division. It'll just take way too much effort. But multiplication is fine. It's the same as for the decimal system, which is to say, if you know how to do addition, you'll know how to do multiplication. It's actually much easier than the decimal system because you only have to ever multiply by 1 and 0, which are the two easiest numbers to multiply by. 1, 0, 1, 1, 1, 0, 1, 0. Let's do this multiplication. So again, it works just like you learned in school. You start with this digit, you multiply it to each one. Okay, so 0 times 1 is 0, 0 times 1 is 0, 0 times 0 is 0, 0 times 1 is 0. So you'll notice if the digit you're multiplying by 0, it'll speed it up quite a lot because you just get all zeros. Then you do another 0 on the next line as a placeholder 0 before doing the exact same thing with the next digit. Okay, so you do 1 times 1, 1 times 1, 1 times 0, 1 times 1. Okay, but multiplying by 1 just provides a copy of whatever you multiplied by. So you're just going to get an exact copy of that top number. So 1, 1, 0, 1. All right, now you need 2 placeholders for the next digit. And then you do the same thing. But now we're multiplying by 0 again. 0 times anything is 0. You're just going to get 4 zeros. And then lastly, I'm out of colors, so I'll just go back to blue. Now you need 3 placeholder zeros. And then you do the same thing. All right, but it's 1 times something, just makes a copy of it. 1, 1, 0, 1. Then you just add down like you would when you multiply numbers as a kid. So this is 0, this is 1, 1, 1. 1 plus 1 is 0, carry the 1, 1, and 1. Okay, so that is how multiplication works. It doesn't get much more complicated, it just takes longer if the numbers get bigger. But if you want to practice more, feel free to just throw in more things like this. But I would say just, if you could do the homework, that's fine. You don't have to do too much practice. You could try to jump to the homework now and see if you could do that. Okay. So the last thing for today is just to talk about a little bit about computers. So I said at the beginning, computers basically, they run on things that have only 2 states, on or off, which sort of act like 0 and 1. So a computer communicates symbols to us via sort of a weird thing, which is we just sort of agree upon something, an agreed upon mapping between numbers and letters. Because the computer can just, it can write any, it could say any number using zeros and ones. That's what binary allows you to do, but how does it say a letter to you? How does it tell you a letter? It's just an agreed upon mapping that has been pre-chosen. So for example, H has been given the number 72 in decimal, which of course the computer would communicate using binary instead. And lowercase h gets a separate thing. It would be 104 in decimal. So really in binary, this 72 would turn out to be like 100100 in base 2, like that. Yeah, so that's going to come up later. We don't have to worry about it too much, but basically there is a name for this. So this mapping is it's called the ASCII. I don't even know what it stands for. Standard. I'll put a link to it on Moodle. And basically, it's just a big chart that you can read off to translate between what a computer would say a letter is in binary, what it's been assigned to, in terms of like storing data and things like that. Okay, so that's it for this lecture.